Hello and welcome along to Lecture 5 on our course on the practice and pitfalls of studying organic reaction mechanisms. Lecture 5 is the final formal lecture in the series, and this time we're talking about catalytic reactions. Now in this final lecture we've left some of the most difficult concepts to last, some of those concepts where most mistakes are made. In catalytic reactions, the first time I heard something like all the processes in a catalytic cycle are running at the same rate, that sort of blew my mind. And if hearing that makes you think, what? Then this really is the lecture for you. I think more than any other lecture in the series, I've recommended once or twice to package this up into smaller chunks than the full lecture itself. Take each part in turn and try not to move on until you are really comfortable with the concepts discussed. We try to tie this into lecture 1 and how we broke up reactions into discrete chunks, discrete steps with individual rate constants. We do the same here, but we build on that for the case of catalysis. So you're almost there. This is the final lecture again. I hope you've enjoyed the course so far. We'll be back one more time for a little bonus lecture that summarises everything. But for now, without further ado, please do enjoy lecture 5 on catalysis. Thank you.
Hi and welcome back to the course on the practice and pitfalls of studying organic reaction mechanisms. This is lecture 5, the final lecture, and this time we're discussing catalytic reactions. Recall that reaction mechanisms and kinetics are related to energy profiles and barriers. In the diagram shown, we show a single step uncatalyzed reaction in red. And you can see that we've marked the transition state barrier, delta G uncat, for the forward reaction. The alternative multi-step reaction pathway shown in blue is what we might expect for a catalyzed reaction that presents an alternative route to the same outcome. However, after the first step, let's presume a binding event to the catalyst, the key transition state barrier is higher than for the uncatalyzed process. In fact, delta G cat is greater than delta G uncat. There is no catalysis in this case. Let's look at a similar case comparing the blue and red pathways. This time, the first step in the blue path, catalyst binding, leads to a key transition state barrier that is similar to that for the uncatalyzed reaction. Again, there's no catalysis here. In this third case, the blue path involving a catalyst appears to lower the energy of the bound reactant and the key transition state barrier. However, when we compare the barriers for the uncatalyzed process, the barriers for the red and the blue processes are about the same size. There's still no catalysis here. Things turn interesting in this last example. Now, the blue path sets up a situation where the key transition state barrier is lower than for the uncatalyzed process. Now we have conditions for catalysis. Catalysis can occur in many different ways. In this first example, in phase transfer catalysis, a catalyst lowers the barrier to moving, usually charged species between phases. In Lewis base catalysis, an amine, phosphine or other Lewis base carrying a lone pair of electrons activates a substrate via covalent bonding. This creates an intermediate that is set up to perform a key transformation, such as in the case of the carbonyl coupling type process shown. Electrophilic catalysis creates conditions under which the key substrate is made more electrophilic than when the catalyst is not present. The substrate is thus poised for attack by an incoming nucleophile. The barrier to reaction is lower than the uncatalyzed process. As a final example, metal ion catalysis deals with binding of substrates to typically transition metal complexes. This enables conformational restraint of the substrate. It can also alter the electrophilicity of that substrate. This type of catalysis is most commonly linked with organometallic catalysis. There are many other examples of catalysis, and we've shown only 4 classes here. In this lecture, we are primarily concerned with how to break up a catalytic process into discrete steps. We want to be able to tackle any type of catalysis the way a physical organic chemist would, regardless of what type of catalysis we actually have in front of us. To start, let's drill down on the definition of what makes a reaction catalytic. Look at the linear reaction on the left. These 3 reactions are similar to the types of processes we considered in detail in Lecture 1. There are starting materials, 1 or more steps, then products. There is a clear start and end to the reactions as they are drawn. In a catalytic reaction, the catalyst itself emerges unchanged at the end of the reaction that delivers the product. So you can see the catalyst on both the left and the right hand side of this reaction. As well as serving to provide an alternative and more feasible reaction pathway to the products versus the uncatalyzed background reaction, catalysts remain unchanged at the end of the reaction. Let's move this one step further. Let's look at drawing catalytic cycles as cycles. The catalytic reaction at the top of this slide is written in a linear fashion, as we saw in the previous slide. The 2 steps have associated rate constants K1 and K2, just like any of the reactions we've considered before. You can tie the left and right sides together using the catalyst species. Notice that the catalyst, denoted cat here, appears on both sides of the equation. So, when we draw the same reaction in a cycle, the catalyst species form the cycle. The reagents and products, the inputs and the outputs, are drawn on the periphery of the cycle. The next part of this process is absolutely key. Do not move on until you are comfortable with this. Because the catalyst species are tied together in a cycle, the rates of all the steps in the cycle are exactly the same. As one molecule of A is converted to A cat, so too is one molecule of A cat converted to one molecule of product. You can think of it like a turning wheel. All parts of the wheel have to turn at an equal rate. We can't have one part of the wheel turning at a rate faster than another. Because it's a cycle, all parts of the wheel turn at the same rate. If all the rates are the same, it is only the rate constants that differ in each step of the catalytic cycle. The step with the lowest rate constant is what dictates the rate of all steps in the cycle, and thus the rate of formation of product. Again, take your time with this slide. it's an important and somewhat counterintuitive concept to think about. And if you have any more detailed questions, please do reach out to me about this. All catalytic species inside the cycle are at constant concentration. We therefore define a turnover limiting step to represent the elementary step possessing the smallest value of the rate constant times the concentration of species involved in that step. We do not use the term rate limiting step in catalytic processes. Another way to think about the counterintuitive nature of catalytic cycles is a roundabout. If the roundabout is jammed with cars, all of them are moving at the same velocity. Each car is moving as quickly round the road as the car in front and the car behind. The cars are only as fast as the cars that move slowest around the cycle. All cars move at the same velocity as the slowest car. Catalytic cycles, like types of catalysis, come in many forms. The first example on the left is the simplest. A substrate A interacts with a catalyst, it forms a bound intermediate, ACAT, then creates the product and regenerates the catalyst. There are two steps in the cycle and thus two rate constants, K1 and K2. The next example is made more complex by the fact that the reaction does not start with the active catalyst. Instead, a pre-catalyst is activated to set up the catalytic cycle. This catalyst activation step is what is called an off-cycle process. The third example shows a case where two reactants are involved in the catalytic cycle. This introduces another step and therefore another rate constant, K3. The final catalytic cycle exemplar shown here shows a rather complicated case that involves multiple on-cycle catalytic steps as well as an off-cycle equilibrium at one step. Each and every step, on-cycle or off-cycle, has its own rate constant. Now, we need to see what these scenarios mean when we monitor the rate of change of the species involved over time. Let's look at a case study with the simplest catalytic cycle. Here, we will consider some concentrations of A, B and CAT, as well as some numerical rate constants. This will help us make the link between the concept of the cycle and the data obtained from monitoring the rate. So, let's consider the case where we are reacting 1 millimolar concentration of A with 0.05 molar or 5 mol% concentration of catalyst. Let's also say that the rate constant have the values as shown. So K1 equals 8.61 milliliters per mole per second and K2 is equal to 0.24 per second. Here we see that K1 is greater than K2. Because the rates of both steps have to be the same, they are tied together in a cycle, then the rate must be dictated by the second step. The second step has the smallest rate constant. In other words, the turnover limiting step is step 2, where ACAT is transformed to product P and regenerates catalyst CAT. Look now at the raw data in the graph at the bottom. Notice that the concentration of A under the conditions stated, decays in a straight line until near the end of the reaction. If we write out the rate expression with the experimental know-how that step 2 is the turnover limiting step, the rate expression can be written as follows. We can say that the rate is approximately equal to K2 times A cat, and because the concentrations of the species inside the cycle are constant, then we can say that the rate is approximately equal to K2 dash, where K2 dash is a new rate constant which combines K2 and the concentration A cat. The concentration of A cat is approximately constant until the concentration of substrate A is very low. So what we're saying overall is that for the majority of the reaction is pseudo zero order in A. For the majority of the reaction, the catalytic species have a constant concentration. The rate expression for this reaction thus simplifies to a constant. That is why the degradation of A occurs with a constant rate in a straight line. Because A does not appear in the rate expression in this case, we say the catalytic reaction is pseudo zero order in A. When A is very low in concentration, the rate of the first step decreases to the point that it dictates the rate of the entire catalytic cycle. Let's now compare this experimental outcome to a similar case in which the rate constants are switched in magnitude. Now, K1 is 0.85 millilitres per mole per second, and K2 is 7.06 per second. Again, the rates of both steps in the cycle are linked and exactly the same. The lower rate constant for step 1 means this step is now turnover limiting. So the process of substrate A and the unbound catalyst coming together to form the bound species A cat. Now, the rate of decay of A versus time is no longer linear, if we look at the graph on the bottom right hand side of this slide. The reaction now exhibits a first order decay in substrate A. When we look at the rate expression and simplify it knowing the catalytic species have constant concentration, we can see that the reaction is indeed first order in A. When A gets to very low concentrations, such that the concentration of A and not the rate constant dictate the overall rate, this still keeps the first step as turnover limiting. Therefore, unlike the first scenario, there is no change in the curve shape as A decays over time. In this case, the first step remains turnover limiting throughout the entire lifetime of the reaction. Instead of looking at concentration of A versus time, let's look at the rate of formation of product versus the concentration of A. This will help with our understanding of this concept of pseudo-zero order in A for the case where step 2 is turnover limiting, and that was on slide 24. Let's consider the case on the left where the reaction starts out with step 2 in the catalytic cycle being turnover limiting. The rate of formation of product versus the concentration of A, the blue dots, show an approximate flat line at higher concentrations of A, reflecting a pseudo-zero order dependence in A. As we scan from right to left along the x-axis, at lower concentrations of A, the rate of formation of product approximates a steep straight line, showing approximately first order dependence in A. Note that at lower concentrations of A, the first step becomes turnover limiting. Remember, the overall rate of a step is judged by the multiple of the concentration dependence and the rate constant. In other words, rate is equal to K times the concentration of species involved in the rate or turnover limiting step to the power that represents the order of that species in the reaction. In a related case study, the rate constants K1 and K2 are now reversed in magnitude. Let's now look at the right-hand process. In this case, the rate of formation of product versus the concentration of A, the blue dots, show a non-horizontal straight line for the entire reaction profile. The rate of formation of product has a first order dependence in the concentration of A for the entire reaction. In this case, even at very low concentrations of A, the first step remains turnover limiting. There's no switch in the turnover limiting step when the first step has the lowest rate constant. If we look at the same case study from the point of view of catalyst concentration over time, we can define another key concept in the mechanistic study of catalytic reactions. The catalytic species preceding the step with the lowest rate constant will be present in the highest concentration of all catalytic species involved in the reaction. This is the catalyst resting state. The resting state can change over time as reactant concentrations change. Look again at the kinetics of the catalytic cycle where K2 is smallest. The catalytic species involved are, firstly, Cat, the catalyst proper, the unbound catalyst, and 2, ACat, the catalytic intermediate with bound substrate A. For most of the reaction, the concentration of ACat is greater than the concentration of Cat, and therefore ACat is the catalyst resting state. When the concentration of A is very low, the first step becomes turnover limiting, and the catalyst resting state switches to Cat. And you can follow this by looking at the graph on the bottom left-hand side of this slide. In the alternative case where K1 is turnover limiting, the concentration of Cat is greater than the concentration of ACat. And because the first step is turnover limiting for the entire reaction in this case, the concentration of Cat remains higher than the concentration of ACat for the entire reaction. In other words, Cat is the catalyst resting state for the entire reaction, where K1 is always turnover limiting. So as you can see from these two cases, the catalyst resting state is the catalyst species that precedes the turnover limiting step. From catalyst resting states, we now move on to another interesting phenomenon in catalytic reactions. To understand this new phenomenon, we need to consider a slightly more complex case. In the catalytic cycle shown on this slide, we have now added a catalyst activation step. The off-cycle precatalyst undergoes a transformation that releases the on-cycle active catalyst. Just like the steps in the catalytic cycle, this catalyst activation step has its own rate constant, denoted K-act. Whilst this precatalyst activation is not in the catalytic cycle, it does dictate the maximum rate of the catalytic reaction. After all, the precatalyst activation step dictates the concentration of active catalyst available. This relationship of the catalytic on-cycle steps and the off-cycle precatalyst activation directly affects the shape of concentration versus time plots. In the case where the precatalyst activation step has a much smaller rate constant than either of the on-cycle steps, we see a significant induction period. That's denoted by the slower parts of the concentration versus time plot highlighted in the red boxes. The rate of the catalytic reaction reaches a maximum only after the maximum amount of active catalyst is released following activation. If the precatalyst activation has a higher rate constant relative to the slowest on-cycle step, the visible induction period is far less pronounced. You can see this again by looking at the areas of the plot highlighted by the red boxes. Another way to understand induction periods and precatalyst activation is to plot rate versus time rather than concentration versus time. The peak of the rate versus time plot reveals the maximum catalytic reaction rate following the precatalyst activation. In other words, the maximum rate marks the end of the induction period. And we can see this plotted on the right hand side of this slide. The next characteristic detail of catalytic reactions we will discuss is the catalyst turnover. This can be defined with two key parameters. Firstly, turnover number, or TON, is the ratio of the number of moles of substrate converted to desired product divided by the number of moles of catalyst employed. Secondly, we have turnover frequency, TOF, which is defined as the turnover number, TON, divided by the unit of time. Please note the turnover frequency should be defined for the conditions under which it was measured and at a given point in time. These parameters help quantify the comparative efficiency of the catalyst, but they are often misused. A definition published in ACS Catalysis helps set TON and TOF in context. Quote, "The turnover frequency, TOF, is a measure of the instantaneous efficiency of a catalyst, calculated as the derivative of the number of turnovers of the catalytic cycle with respect of the time per active site, at such a low concentration of the catalyst that exhibits infinite dilution behaviour and the reactants and products are, if possible, at a saturation regime. All the influencing conditions should be properly declared, such as the concentrations and temperature." We are now in a position to revise the most important natural and applied case of catalysis often taught at undergraduate level, enzyme catalysis. We consider the simple schematic on the top of the slide. An enzyme has an active site in which to bind the substrate. The enzyme and substrate are in a bound and unbound equilibrium. In the bound state, the substrate can be transformed to the product, which is then released, revealing the enzyme catalyst once again. We can express this schematic in the form of stepwise reactions with individual rate constants. This kind of process is similar to how we discussed steady state and pre-equilibrium kinetics in Lecture 1. As we covered in earlier slides, we can tie the left and right sides together in a cycle because the enzyme is released at the end of the reaction. We can then redraw this reaction sequence to show the enzymatic, i.e. catalytic, species in a cycle, and the substrate and products outside that cycle. Now, slides 38 to 49 contain some equations and concepts to do with enzyme catalysis. This will require some dedicated concentration, so it's recommended you watch this part of the video separately, if possible. We can now work through how we would express the equations for such an enzymatic process. Firstly, we assume that step 2 in the catalytic cycle is turnover limiting, such that the rate of formation of product is approximately equal to K2 times the concentration of substrate bound enzyme ES. We then apply the steady state approximation that we learned about in Lecture 1 with a slight twist. In Lecture 1, we learned that we can apply the steady state approximation to cases where the rates of formation and decay of the intermediate are such that the concentration of the intermediate is approximately constant over the course of the reaction. The enzymatic, i.e. catalytic, variation on the steady state approximation comes from the fact that all the steps in the catalytic cycle are running at the same rate. ES in the enzymatic case is like A cat in the case we covered on slide 28. Next, we rearrange the equation from the steady state approximation and define the concentration of ES in terms of E and S. At the same time, we define uppercase K subscript MM, the Michaelis-Menten constant. And that's named because this model of enzyme catalysis that we're working through was first developed by Michaelis and Menten and is termed most commonly as Michaelis-Menten kinetics. Next, we define the total concentrations of the known species, the enzyme and the substrate. So E subscript naught is the total concentration of enzyme, and that's approximately equal to the concentration of unbound plus bound enzymatic species. S subscript naught is the total concentration of substrate, which is the concentration of unbound and bound substrate, but because the concentration of bound substrate is so small, we can approximate the total amount of substrate to be simply S. This allows ES to be expressed in terms of total concentrations of the known species. Next, we use the new expression for ES in the expression for the overall reaction rate. So where we started by expressing that the rate of formation of product was approximately equal to K2 times ES, we can now substitute the new expression for ES to give the Michaelis-Menten equation. So, the rate of formation of product P in this enzymatic process can be expressed in the equation shown at the top of this slide, as derived on slides 34 to 42. We're now going to see how this expression can be used to define some useful quantities in the study of enzymatic processes. Firstly, we can define the maximum rate, Vmax, when the magnitude of the concentration of S is much greater than the magnitude of Kmm, where we say that Vmax is approximately equal to K2 times E naught. The rate can be expressed as a fraction of the maximum rate, and we can see that in this next equation, where we've divided the Michaelis-Menten equation by K2 times E naught. If we rearrange this latest expression into a linear form, you get the Lineweaver-Burke relationship. When plotted, this gives the now infamous Lineweaver-Burke plot. By plotting reciprocal rate versus reciprocal substrate concentration, we get a convenient method for extracting maximum rate and the Michaelis-Menten constant, which, in simplest cases, is thought to approximate the substrate enzyme binding constant. In effect, we start by plotting rate versus concentration, which, when read from right to left, reveals a pseudo-zero order process with respect to the concentration of substrate at higher concentrations, and a first order process with respect to the concentration of S at lower concentrations. The use of such plots goes much further, but in the context of this introductory course, we won't go any further for now. If you have any more questions about enzyme catalysis or the derivation of a Lineweaver-Burke plot, please do reach out to me. Michaelis-Menten enzyme kinetics showed that plotting rate versus concentration could give useful information beyond standard concentration versus time plots. Discussion on induction periods on slide 32 also revealed some use of the more unusual rate versus concentration plots. Reaction progress kinetic analysis, RPKA, generalizes rate versus concentration graphs through graphical rate equations that can help analyze more complex systems, for example containing two substrates or induction periods. As a brief introduction to reaction progress kinetic analysis, we will cover some of the really valuable experiments and outcomes that can be derived from this approach of plotting rate versus concentration. Firstly, we can define what is known as a same excess experiment. Consider the palladium catalyzed Heck reaction as an example, and we have a specific example shown at the top left of this slide. If we conduct this experiment at two different starting concentrations of the substrates, but keep the excess of one substrate over the other the same, i.e. the same excess, then we are essentially able to make the catalyst do more turnovers to the product. If you look at the graph on the right hand side, we co-plot reaction 1 and reaction 2. In the plot of rate versus RL bromide concentration, the fact that the lines from the two experiments overlap means that there is no catalyst deactivation occurring. This can be distinguished from the case of product inhibition, where the product formed poisons the catalyst that made it, by a third experiment in which product is added from the start of the reaction. If there's no change in the curves, when product is added from the start, then that indicates there is no product inhibition. If we consider a second case of a cobalt catalyzed epoxide hydration, similar same XS experiments show that the curves for the two experiments at different starting concentrations of the substrates do not overlap. Look at the graph on the right hand side. The pink line and the blue line do not overlap. From this, we would be able to conclude that catalyst deactivation or product inhibition is occurring. And if we want to find out if the lack of overlap in these lines is down to product inhibition, then we would do a third experiment where the product is added from the start of the reaction. Going back to the HEC example from the previous slide, we can add a different XS experiment. The difference in RL bromide and olefin concentrations is either the same or different. For example, the difference in RL bromide and olefin concentrations is either the same or different. For example, the starting RL bromide concentration minus the starting olefin concentration could be 0.12 molar, then 0.08 molar, then finally, the same as the last experiment, 0.08 molar. In the top graph on the right hand side for rate versus time, we notice 2 points. The maximum rate peaks approximately 5 minutes after the start of the reaction, indicating that there is probably an induction period in catalyst activation process. Secondly, the maximum rate achieved increases from the blue to pink to green line. But what is causing the increased rate here? Plotting rate divided by olefin concentration versus the concentration of RL bromide shows horizontal lines in all three cases. And you can see this on the bottom graph on the right hand side of this slide. The reaction is pseudo-zero order in RL bromide. The second step in the catalytic cycle shown on the bottom left is likely to be turnover limiting, and the oxidative addition product shown at the 6 o'clock position on the cycle is the catalyst resting state. You can read a lot more about the RPKA methodology at the references provided. That brings us to the end of the lecture. In summary, we started by understanding the concept of catalysis from the point of view of potential energy surfaces. We then spent some time getting to the idea of catalytic cycles turning like gears so that the catalytic species were counterintuitively running at the same rate. The catalytic species inside the cycle have constant concentrations. And following an extensive revision of some enzyme kinetics, we saw how RPKA has become a highly valuable tool in the modern interpretation of catalytic processes. So thank you for watching Lecture 5 on catalytic reactions. We've now completed all 5 lectures in the course, and you're ready to tackle the assignment laid out in the intro lecture 0. We'll have a final summary video of the lecture series, but for now, thank you for watching this lecture and thank you for taking part in the entire course. Very well done. Thank you.